Right, I love this chapter. This chapter isn't necessarily the longest chapter, but it is one of the most interesting chapters. There is a ton of stuff about to happen. People are asking me how far I expect to get through this material. I don't know. I'd like to get through all of it. I doubt I will, but I'll try and get through as much as I possibly can between now and the end of next Wednesday, and then you'll get tested on it. So this weekend's pretty busy, lots of things to do. You've got, I imagine, other exams next week, so be good, get your work done, and hopefully it'll pay off next week. The key here is that benzene is not an alkene. It's not a simple alkene, even though we still draw it with 3 pi bonds. Okay, we decided that that wasn't particularly accurate, but we still need to have some electrons to push around. So you will see benzene written as this at the bottom. You will see benzene written as the sort of kekulé structure when we start doing reactions soon. But the key here is that it doesn't do the same reactions that alkenes do. You do not decolorize bromine if you add bromine to benzene. It just isn't reactive enough. And the idea is because it's 6 pi, all the pi electrons live in the stable molecular orbitals, the bonding molecular orbitals, and it doesn't want to react unless you make it. We will persuade it to react, which is the whole point of this chapter, but so far we can differentiate it from simple alkenes by saying that it doesn't do those reactions that alkenes do. What we will do is now brominate, alkylate, acylate, nitrate, and sulfonate. There are 5 typical reactions that everybody learns in this class that benzene is very good at to put the first substituent on. So what I expect to get through today is the first substituent. And then if you go back and look on some of the slides from the previous chapter, the derivatives of benzene that were useful had multiple substituents, maybe 2 or 3 or 4. So when we get through the first substitution and we have what we call a directing group attached, we then have to worry about where the next group will go. Will it go ortho, will it go meta, will it go para, or mixtures of all of them? And that's pretty heavy, right? There's a lot of heavy stuff to come. It's just circumstantial that it's before the exam, but this is a real test. If you can keep up with this stuff and do well, then you're pretty set for the future. What we need to do here is to make benzene want to react. So you really can't do much with benzene itself. You can't shout at it. It won't react faster if you shout at it. We've tried. It doesn't work. So what you can do is make its reaction partner more reactive. You try and make the halogen, for example, more reactive. If bromine doesn't react on its own, come up with some solution to help this reaction out. Now, people might say, well, why not just heat it up? You can speed things up by heating things up. But what happens to bromine when you heat it? You get radicals. It breaks into 2, right? And that's not going to give us the chemistry we want. In fact, all of these reactions that you will see today are electrophilic reactions. That implies positive things and negative things. So if we want to avoid radicals here, we can't heat this thing up. That's not a way to speed the reaction up. So what we'll start doing now is a whole bunch of catalysis, a whole bunch of reactions in which we will pick up some little piece, in this case iron or a derivative of iron. It will coordinate with the halogen, make the halogen more reactive, and so benzene has to get involved. It's not that benzene wants to get involved, it has to get involved because for the benefit of the overall system. So what we'll see here are typical conditions for the bromination of benzene. Now this is useful because you go back to some of the Grignard stuff that we did. We had not made bromobenzene before. Now we have a system where you can start with benzene itself from crude oil, and then you can put bromine on it, then you can make a Grignard, then you can make an alcohol, then you can make a ketone, and you can go back further in terms of retrosynthesis. So what's happening here is the iron is behaving as some sort of catalyst. And what you'll see on most exams and most websites and stuff like that is that iron reacts with Br2 to give FeBr3. And FeBr3 is the active catalyst. Iron, similar to things like aluminium, similar to things like boron, has empty orbitals. And so it can behave as a Lewis acid. And what it will do is coordinate with the bromine and make the bromine, the bond will stretch, the molecule will become more reactive, and it will then react with the benzene. So they're the conditions. You can either add FeBr3 or Fe, same thing, and you get this result. Now what's happened here, you've got to be very careful. What has happened is that the product contains a bromine in place of a hydrogen. So we're not necessarily just adding anything, we're actually substituting something. So this is a novel system that you haven't seen before, but I think it is made up of things that you have seen before. It starts out with an addition and then ends up with an elimination. Okay, we've seen those in individual reactions before. That's all it is. If you understand that, this isn't that difficult. So if you want to make bromobenzene, take benzene itself, add bromine, add the catalyst, and away you go. You get a decent yield of bromobenzene. And then we're into things like spectroscopy. How can you tell it's the right stuff? Look at the mass spec. You expect to see N plus and N plus 2, and the ratio should be 1:1 because of the isotopes. You can really pull all this stuff together now. These are the reactions you will see today. And I will say this a couple of times. It is the same mechanism every time. If you are trying to memorize this stuff, this won't work here. right? It'll be painful and it'll be unnecessary, because the way we get these products in each of these reactions is the same. Yes, the electrophile will change, but it will be generically the same thing, where we're adding something positive to the benzene ring, doing an addition, then an elimination, and getting the substituted product. So make a note of that. These mechanisms all are very, very similar, right? You don't need to learn it 5 or 6 times. So we will make bromobenzene. We'll show you the mechanism for that. Analogously, you can see there, you've got the chlorobenzene. It's the same type of chemistry. Nitrobenzene you haven't really seen. We haven't talked much about the nitro group, but it's very, very powerful in terms of its properties, in terms of electron withdrawing ability, and also the ability to bring nitrogen into these molecules. So that's a very important one. Sulfonation isn't so important, but we can actually use the SO3H group as a protecting group, right? We can block positions with that group, and that will be useful because that process will be reversible. And some of the ones that you'll scratch your heads about are alkylations and then acylations. And we'll find that what we call the Friedel-Crafts Alkylation often isn't very useful to make alkyl benzenes, and we have to go around and sort of do this in a longer process where we acylate and then reduce, but that reaction is much more efficient, and we'll see why that's the case today. So what we're going to do here is a whole bunch of substitutions, and they happen to be on aromatic systems, so we'll call them aromatics, and they happen to involve electrophiles, so we'll call them electrophilic aromatic substitution. So to get started on this, go back and look at addition reactions of alkenes, and think about the driving force. Why were these things allowed? Why were these things good? And the answer usually is because you're swapping pi bonds for sigma bonds. That's always a good thing because those sigma bonds tend to be more stable. And the pi electrons are quite weakly held. They're not as tightly held as sigma electrons because they're further away from the nucleus. So in the first step of any typical electrophilic addition, let's say HBr, something like that from last semester, or Br2, the nucleophilic pi bond went after the electrophile. Typically it was a delta positive E. There's some element Y that's wanting to break off as a leaving group. And so we had a nucleophilic attack of the double bond onto the electrophile, and the leaving group broke off. Those are simple things that you know in depth. This reaction tended to be enthalpically favored in the sense that the products were more stable in the starter materials because you've now got sigma bonds where you had pi bonds. And also they tended to be entropically disfavored. After the Diels-Alder reaction, this should mean more now. Okay? You're bringing 2 pieces together and you ended up with 1 piece. That tends to be entropically disfavored. Right? But the reactions work because delta G overall works in terms of being negative, and these types of systems were good. And the products that you got were through carbocations, and they were addition products. Right? So now the question is, why doesn't benzene simply do that? If that's so good for alkenes, why doesn't it work for benzene? And the simple answer will be, you want to get that benzene ring back. Why? Because it's stable. It's aromatic. It benefits from having all its electrons in the pi bonding orbitals, and so therefore we want to get that benzene back. So we'll only use it temporarily in chemistry, in reactions. Now, the whole point of this is EY is very reactive. Not that the benzene is any more reactive. You can put something in its presence that's very reactive, and the benzene just has to play along to get to the system to become more stable. So what we'll do again is challenge the benzene with a different type of with electrophiles, and some of them work and some of them don't. Bromine on its own doesn't work. It does for alkenes. And we'll find now that the first process here, the first step, is very similar. You take a pair of electrons from the pi bond, and you go after the delta positive part of the EY system. Okay? And if that happens, the Y thing breaks off, and Y tends to be electronegative, tends to be a good leaving group. And after that, you can imagine you've taken away 2 electrons from this system, so we ought to generate a positive charge. And that positive charge is no longer a simple carbocation that just benefits from hyperconjugation like you see in the alkenes. This is now a step further from the diene that we did. When we did the diene and we added bromine or HBr, 1,2 and 1,4, you produced a resonance stabilized carbocation intermediate. And that carbocation is much better because of the pi bond and the allylic system, and that's why the reaction barriers were fairly low. This system benefits even more. You've got more possibilities here in terms of resonance, and you will spend a lot of time the next week drawing resonance structures. Okay? If you're not happy with resonance structures, get happy. Here's where things differ. Here's where the mechanisms diverge. In the last slide, or on the last slide, Y minus behaved as a nucleophile, went after the positive charge, and gave you an addition product. Now what we're saying is that doesn't happen. In this second step, what does it remind you of? You've got a carbocation, you've got a base coming after the beta hydrogen, and you're getting an alkene. What mechanism is that? That's E1. Good, it's E1, right? So you're doing a simple electrophilic addition, and then you're doing an E1 in sequence. So therefore, really, it's not a new mechanism. You just put things together in a sort of a modular way. Well, the whole driving force here is to get that 6-membered ring back with those 6 pi electrons. So think of that. You're saying now that the benzene ring is even more stable than having 2 extra sigma bonds. The benzene ring wins, and you want it back. So what we'll see here now is some idea of the rates of things, some idea of the reaction profile for how this works, and then we'll put it into practice with different electrophiles. Now stop me at this with this stuff. It gets very busy very quickly. Stop me with questions if you can. Now, here is a reaction profile for a typical electrophilic aromatic substitution. And E here is still generic. But what I suggest is that you keep an eye on the fact that the only thing that will change in these reactions is E. Your job will be to work out how to make E and then to be able to use it in the system, in the mechanism. But the mechanism will be the same all the way through. What's happening here is we are starting off with simple benzene. You have a bottle of it in the lab, and you have a bottle of your electrophile. And you put the two together and we get chemistry. EY might be reactive enough as it is, or you might have to produce some species along the way that becomes so reactive that benzene has to get involved. So what's going to happen here is simply a pair of electrons from the benzene ring goes after E, and that bond starts to break. Now, we spent a significant amount of time last semester trying to construct reaction diagrams and also the transition states. Nothing here is any different to that. It's all the same stuff. In fact, you have drawn very similar transition states in the past 6 months. So I expect you to be able to do these. At the top of this barrier, it's obviously a multi-step process. It's not concerted. In the first step, we produce a transition state in which the E is starting to bond to this carbon, and we're starting to generate some positive charge down here. And this is fine because we're building up allylic systems, which are delocalized, and so this charge is fine. We then collapse. This thing breaks apart with Y breaking off, and that gives you this. Now, we've spent plenty of time talking about the ability of Y minus to behave as two different things. It can behave as a nucleophile, but also it can behave as what? A base. Any base is a nucleophile, any nucleophile is a base. Now, in this system, it's behaving as a base. In the addition with alkenes, it behaves as a nucleophile. Fundamental difference. So now we have this idea that whatever's left over can go after this. Sometimes this is water that goes after it, depending upon what you have around. And we're trying to give this system its pair of electrons back. So that is nothing more complicated than a simple E1 process in which you go after the beta proton, and the pair of electrons that were holding the proton to the ring are then used to give back to the pi bond. And you get your six-membered ring back. So we see two steps. It looks an awful lot like an SM1 profile. Very much. It looks like an E1 profile. Yeah? Nothing too complicated. And what we end up with, hopefully, is a more stable product, and that's going to be useful. So there's your classic diagram. You're not going to see dozens of different diagrams in this chapter. You're just going to see the one. That's pretty much it. You will see diagrams next to each other. Once we've got this group on there, you'll have to talk about rates of reaction of the different species and where the next substituent goes, but that's the basic reaction profile. You can handle that one, you can do this chapter. Anybody got any questions? I guarantee you'll have questions at 4:55 next Thursday afternoon when I'm trying to get home. And play with my new dishwasher, which I'm buying tomorrow. What an exciting weekend, I'm buying a dishwasher. How does it work? Well, you can see different mechanisms for this around. You can see, or slightly different. Let's be careful, slightly different. There's the setup. There's the clue. That's what you're looking for. You have a benzene system. You have bromine. You have Fe or FeBr3. They do the same thing. And you're ending up with a bromo system. That's a classic way of putting a bromine into a benzene ring. Well, how it happens, first off, is by activation of the electrophile. We've already said that bromine itself is not reactive enough to work. So we have to make it more reactive to do so. And what's happening here is that FeBr3 is behaving as a Lewis acid. It's absorbing a pair of electrons, accepting a pair of electrons because the bromine has plenty. And if you stick these two pieces together, you form an activated complex. An activated complex looks like that. So what you've got now, really, is a Br2 molecule stuck to FeBr3. And what that does is shift the electron density. You'll find now that ultimately it's this terminal bromine that's losing out electron density. Okay? You think about taking electrons away from bromine, it's an electronegative element, it wants them back. So we'll see a shift in electron density. Now, people will ask me this question, so we'll get it out of the way now. That arrow there is the same thing. We've just pushed a pair of electrons from the bromine and stuck the bromine to the Fe. Some people suggest that it happens like this, where you break apart the Br-Br bond and you get Br+. Okay? That's in the textbook, and I don't think they use that in the mechanism in the textbook, but that structure is shown in the textbook, and I've seen it in other places. If you like that, fine, go ahead. The stuff I've drawn on my website doesn't do that. It attacks, the benzene attacks this thing. Okay, but either of them are fine. So what we've set up now is a good electrophile. This, in the bigger scheme of things, as we're trying to catalog this stuff today, that is your E+. That's what you need to attack. So next arrow, to try and get this thing going, I think what we want to do is attack that, and then the rest of it breaks off. That's the attack on EY to produce the activated complex. So the next slide is simply the whole thing. If you put this next to the generic picture we just drew, it's the same. Sure, EY is now Br2, and we've added the Fe to try and sort of enhance the electrophilicity of this thing, but it's the same mechanism. And what we get down here now is the stabilized carbocation, and I have to show the fact that that is stabilized by drawing resonance structures. That's absolutely essential here. And as we progress into the multiple substituents, you'll end up drawing 4, 5, 6, 7 different resonance structures to be thorough and show that this thing is decent. This is a decent carbocation. Then what we get is the elimination from that molecule, from that carbocation in the second step, and that gives you the product. Now, which of those steps is rate determining? Formation of the cation or loss to give the product? Formation of the cation, as it usually was, right? E1, SN1, it was usually the formation of the cation. That was the slower step, and then you end up with a fast step going to product. And don't forget, acid-base reactions are usually fast, and away we go. Now, there's something interesting here. If you think about what's being used as the base here, technically you're using Br-. So the product, the byproduct here, is Br and H, HBr. Now, is that a strong acid or a weak acid? Very strong acid, right? Keep an eye on that. That is a very strong acid. And that is simply an acid-base reaction. So you can talk about, not necessarily pKa's, that's very difficult to measure here, but you can talk about relative strengths of acids. This reaction, if I go back to that graph, is way downhill. That second step is way downhill. So that says in my mechanism here that this material is heavily favored. Right? That material is heavily favored. So if this is a strong acid, how weak of a base is Br-? Very weak, very, very weak, right? So if Br- is strong enough to take off this proton, how acidic is that proton? Incredibly acidic, right? It's incredibly acidic. Why is it so acidic? Look at the product you get. It's an aromatic system. So I don't know if that made any sense. It'll be on YouTube later if you want to think about it again. But that indicates how good this system is and how badly it wants to go back to being aromatic. The fact that something as weak as Br- can take off that proton in an acid-base reaction and give you the benzene ring back. Okay? Thermodynamically, it makes sense. It adds up. So what we have now is a very simple mechanism, very simple synthesis of bromobenzene, which will become very useful as we progress towards doing synthesis with these compounds. Anybody want to say anything? Brianna.
Is there ever like a chance that the Br- could have like a positive charge?
Well, that's this next slide. That's exactly that. And the answer is it could. The Br- is a leaving group, so it can break back off. And if it's in equilibrium, it always goes to the more stable product. And the more stable product here, without a doubt, is the benzene ring. So that covers that, right? If you do add, you get this. Yes, it's a diene. Yes, it's nice. Yes, it's somewhat stabilized, but it's nowhere near as good as that product. And we proved that with some experiments previously with the graphs, with the energies, talking about hydrogenation energies, stuff like that. That benzene ring is, you want it back every time. Mr. Homan. This is, yeah, I mean, that was lower barrier, isn't it? So that looks like a kinetic type of outcome, and this looks like a thermodynamic type of outcome, yeah. And the driving force here for the thermodynamic outcome is so big. In restation, we talked about what governs thermodynamic versus kinetic, and you see the gap there between those two? That's not coming back. I mean, that's going to go to the benzene, it's there. It's stuck. It's a big gap. Okay? So now we've got an idea of why we can make, or how we can make benzene do these reactions. We need to enhance the electrophilicity of the other component, and that's all we do for the rest of today, is change that electrophile. And you end up with 5 different patterns, 5 different reactions that give you very useful products, especially in pharmaceutical chemistry, through the same type of process. We shall prove that. If you want to chlorinate, now you've got to be very careful with the language from now on, because people will say, well, bromine's more selective than chlorine. And that will mean absolutely nothing here. Why not? When was that used? What context was that used in? Radical chemistry. This is not radical chemistry, so this doesn't matter. We're putting on a bromine atom, we're putting on a chlorine atom, but we're doing it through a positive electrophilic type process, not a radical process. So what's going to happen here is the use of Cl2. It's a little bit more difficult to do in the lab because Cl2 is a gas. You have to bubble it through the reaction mixture. And we might swap the Lewis acid for AlCl3. AlCl3 will see a lot of. Right? Somewhat tricky to work with because it's so reactive with water, but if you keep it dry, this is a very good Lewis acid. You dissolve these things up, you let the reaction go, and you end up with a pretty decent yield of chlorobenzene, the same way you did for bromine. And if you took the mass spec of this, you'd see the M and the M+2, and you'd see a 3-to-1 ratio. So you can think of, how my mind works and how I'm thinking of next week, all these little clues to help out, all these little parts of problems where you can put all the chapters together and start to think like a chemist. What's going to happen first? Well, the answer is that chlorine doesn't react on its own. It needs some help. So this, again, is a Lewis acid. It accepts electrons. So what we're going to do first is coordinate those two pieces together to produce, in this case, an electrophile. Now, I don't think anybody writes Cl+. I don't think anybody writes a naked sort of Cl+, because it's so electronegative it doesn't want to lose its pair of electrons. But you can certainly write Cl delta plus, right? Cl delta plus, we're going to attack on this piece here so that this chlorine gets its electrons back. So it's very similar to the previous picture where we had the Br2, now we've got Cl2, and we attack at the end, and that gives us a nice simple reaction. So what's this behaving as? What's this behaving as? What's benzene behaving as in these reactions? Nucleophile. It's giving electrons away. It's a nucleophile, or a Lewis base. And if we do that on the chlorine molecule, we have a nice electron flow here where both chlorines end up being neutral. They get their electrons back. And we end up with the same sort of sigma complex we got for the bromine. We just change the Br to Cl. Now we can see that loss of the H again is going to be favorable because the system is so stable when we go back to the cycle. And again, an indication of how acidic the proton is on the benzene system down here is that we produce HCl. HCl itself is a powerful acid. But that tells you that the proton on that sigma complex down at the bottom, this proton right here, that thing is so reactive, so acidic, that even chloride will take it off. And again, you end up with this, which is the aromatic substitution product. Yes? No? Maybe? Next Friday? Hope so. Okay. Now, there's the general mechanism. The book will keep hammering on the fact that this is a general mechanism. You'll see those structures at the bottom in each of these mechanisms. It's all the same. All you need to worry about is the electrophile. How do you generate the electrophile? What is the E+? And how then do I attack? But it's the same generic mechanism all the way. First initial attack, formation of this localized system, the sigma complex, and then loss of that proton in the last step to give you the product. It's the same again and again. Okay. Now, one of these reactions that's very useful, I think, in pharmaceutical chemistry is sulfonation. And this reaction is a little bit controversial in the sense of the mechanism is some people write it one way, some people write it another way. I'll explain why. And this works when you have not just sulfuric acid. Sulfuric acid itself isn't strong enough, isn't reactive enough. H2SO4 is not reactive enough. Because what's happening here is you're picking up this. And that looks to be the conjugate base of sulfuric acid, right? But we're attacking at sulfur. Now, fuming does not mean it's particularly annoyed. It means we've bubbled SO3 to it, right? It looks annoyed when you see this stuff. It's like something out of a horror film, right? You bubble SO3 into sulfuric acid. That does not sound particularly pleasant. I would not want that job. That's why you stay in school, right? And you get SO3, H2SO4, and this then allows for the swapping of this proton here for SO3H. Now, we've seen sulfonates, we've seen sulfonic acids, things like that. It's actually benzene sulfonic acid is a very useful material for us in the organic lab because it's an organic equivalent of sulfuric acid. If your reaction requires a strong acid, you could use the one on the right because that's an organic soluble version, maybe, of sulfuric acid. Well, the mechanism here, this is what the book tells you. You'll see on my slide, I think on my website, on my video, it's slightly different, but you get the same place. What is reacting here is this stuff, SO3. Now, SO3, what can you tell me about sulfur in the middle of that SO3? It's big, but what else? It's surrounded by oxygen. So what can you tell me about its electronic properties? It's very positive. It's very positive, okay? Now, it turns out that you do get some SO3 and sulfuric acid, because H2SO4 can collapse to SO3 and H2O. But there's not enough in it to make it react quickly enough. So we dope this thing by bubbling the SO3 into it and make it react faster. And the initial attack, again, this simply is E+. SO3 now is E+. And if I attack that, and I push 2 electrons onto the oxygen, I make the sigma complex. And now I can draw my resonance structures to show why this is so stable. And then I need to lose a proton. And in the last step, think about this. What type of base is that? Is that a strong base or a weak base? That's a super weak base, right? It's very, very, very weak. So it's strong enough, actually, to take off that proton and go to the product. And then in the last step, pick up a proton from the sulfuric acid mixture, and that gives you the sulfonic acid product. Now, that's the way the book describes it. I'm fine with that. That's fine. I've seen other people do it that way. I've also seen other people do it this way that I'll show you. On my website, I think what happens first is we protonate this guy. Because if you protonate something, you make it even more reactive. So the only difference is where the protonation happens. In this, the protonation happens at the end. In my mechanism, the protonation happens at the beginning. If you want to come by and sort of discuss that, that'd be great. I don't care which one you do. I like the one that I just described second. I like mine because it sets up what's to come after we come back from spring break, which is a whole bunch of protonations of carbonyls that make the carbonyl more reactive, and it fits this same paradigm. But you be happy with whatever. That's the way of putting a sulfonic acid group on, and when we get back, probably after the break, we can use that group as a protecting group and take it off after we've done something else. So keep an eye on that. But arguing here the fact that the mechanism is the same, all you have to worry about is how to make the electrophile. So that's 2. Halogenations and sulfonations. I said I'd get through 5. I should get through 5. Here, we have something that is, I mean, this fascinated me as a kid. For some reason, not too far away from my high school, when we were taking our junior level and senior level chemistry classes, there was a Nobel explosives plant, right? So you realize that Nobel was famous for explosives, right? And they called the division of ICI chemicals the Nobel explosives plant. It was a mile and a half away from my high school. You know, good idea building it next to a high school. But one of the uses of nitration is to make TNT, is to make explosives, right? Nitro groups are actually quite high energy systems, and they do blow up. And if you were to, you know, I'll just, as an aside here, if you were to put a methyl group on here, and then you put another nitro group down there, and we'll do this maybe next week, maybe when we get back. What is that? TNT, trinitrotoluene, boom. Okay? Now, what fascinated me as a kid was we were told these stories that this was now a high explosive. And we did this mechanism in high school, and it was like, cool, that's great. But then the teacher would say, well, all right, but then on the flip side, you get rid of that nitro and you reduce it down to an amine, you're straight into pharmaceutical chemistry. So that one functional group, that nitro group, ties together incredibly destructive explosive chemistry and also medicinal chemistry, pharmaceutical chemistry. So this nitro group is invaluable, I would say, to get nitrogen into your systems. And once we've done that, we can reduce it. So what you should get from this slide is that the conditions required are not particularly fun. This is nitric acid that you use in the lab, right? This is not the expensive stuff, but the dangerous stuff. You do not want to get this stuff on yourself. But it turns out nitric acid is not reactive enough to make this work. So what do you put in? You put in sulfuric acid, right? I mean, this is like mixing evil with evil. And you get this mixture. And that then is good enough to be able to do this nitration. And I'll show you the mechanism for this. It's a weird one where we have a very powerful acid protonating another very powerful acid. But what it gives you is NO2. And the key here, before I go on to the next slide, the electrophile we need here is NO2+. So those of you who like to make flashcards, that needs to be on it. You do need to know how to make this. You do need to know the arrows to push to get to this NO2+. But once you're there, guess what? That's E+. Go after it, do the same mechanism, you're home. That's it, you're done. So this reaction at the bottom, I think it's in our new textbook, and there's no mechanism required for this. It's in organic chemistry, beyond this class. But we can take iron, metal, or zinc metal in the presence of hydrochloric acid, and we can reduce NO2 down to NH2. You need to know that reaction. That's a gateway into an awful lot of stuff between now and the end of chapter 23. You'll be able to do all kinds of chemistry with that particular type of product. So know that product. So you'll need to know the mechanism for the top reaction, but not the bottom one. Are you happy to be back in mechanisms? I thought so. Good. Right, here we go. This is, I think, pushing the limits of with these mechanisms, right? These reactions. Nitric acid is a very, very powerful acid, but we don't need it here for its acid properties. We need it here to produce NO2+. And it turns out it doesn't work unless you have the sulfuric acid in there as well. So I would argue, you think where you started in freshman chemistry coming into this class, and you have some good idea of reactivity and the framework of how the periodic table works. I think this is a remarkable reaction. Yeah, this is one that requires one of these things. That is a very, very powerful acid, and it is being protonated by a very, very powerful acid. What happens here is the hydroxyl group of nitric acid, and you do now need to know what nitric acid looks like, and sulfuric acid, so you can draw these things. I argue you should know those coming straight out of high school or the freshman classes. You need to know those structures. They're very important. What's happening here is we're protonating this. And what's the whole reason to protonate a hydroxyl group? What's the whole sort of motivation to do that? Make it a better leaving group. You want to make it a better leaving group. So we have this species now, which is protonated nitric acid. It's the conjugate acid of nitric acid. Yeah? I mean, that's right, Sammy. Whatever face you just made is exactly right. That's different. Now what's going to happen is this thing is unstable, it'll collapse. And it'll collapse this way so that we don't break any octet rule, and we end up with the nitronium ion, which is the E+. That's the electrophile. And that's what we have to go after. So now, same question. Tell me about the nitrogen. Very positive. It's not only formally positive, but it's attached to two very powerful electron withdrawing oxygens. That's a very electrophilic nitrogen. So my E+ is now here. Once you've got that, and you'll generate that simply by drawing those arrows, you go after it. So that first step of that mechanism is identical to the first steps that we've drawn so far. We produce a sigma complex. Now it just happens to have NO2 attached, where before it had Br or SO3. And we get this thing now, we can draw these wonderful resonance structures to describe exactly how stabilized this thing is, but it's still a carbocation, and we still want that benzene ring back. So now we have to go after a proton and do it. Now, all of a sudden, we've got some water involved. Where did that come from? It's come about maybe by loss of that piece up there, but also what are we making when we make sulfuric acid and nitric acid? What is the solvent? Water. Right, so there is water in there, even though maybe it's not written for you. You should know that stuff by now. So we have a base here, and the argument here is that water is probably the strongest base that we have in there, because what's the pKa of the conjugate acid of water? Negative 1.7, and the pKa's of nitric acid and sulfuric acid were much more negative. Okay, so now this is probably the strongest the strongest base in there, and that goes after that and takes off that proton, and we are finished. And we have the electrophilic aromatic nitration of benzene. 3. Anybody want to say anything before I move on to the difficult ones? Chris, you all right? It's Friday. Spend all day tomorrow shopping. Michael, go on. Nitric acid. I'm not sure I would have any possible mechanism for that, because if I do this, and I'm going to get rid of this in a second, I'll end up with a 6 electron nitrogen. Yeah, so that's not so good. That makes it worse, if anything. So get rid of that. Yuck. So we've done halogenation, we've done sulfonation, and now we've done nitration. And those 3 will come back all the way through this chapter and the rest of the 2 semesters as methods for doing exactly that. Putting on a halogen, putting on a nitro group, putting on an SO3 group. Those are now key to the rest of the term. Now this story. These are named after chemists. I believe they're American chemists who developed them. Incredibly useful industrially. These are processes that are done on multi-ton scale across the world, and they produce alkyl and acyl benzenes for further use. We have some problems with this. This happens to be an alkylation. So you'll see this referred to as the Friedel-Crafts Alkylation. And when I'm done here in a second, I will go and do what's called the Friedel-Crafts Acylation. You absolutely have to know the difference. One involves a carbonyl, one doesn't. So here I have the alkylation version. And you will see, whenever you take this class, wherever you take this class, that this is discussed as being problematic. This is a reaction that works incredibly well on paper, as everything does. But if you try and run some of these experiments in the lab, you get mixtures and it's rubbish. And mixtures are expensive to separate, so we usually don't do these reactions. Well, let's do this one. Let's start off with a tame one that does work. Let's think about AlCl3 and chlorine here. In the same way it reacted with Cl2, that chlorine is sticky. That chlorine has lone pairs. And so if you put this in the presence of a Lewis acid like AlCl3, you will get communication between those two compounds. The chlorine of the alkyl halide will coordinate to the AlCl3. And what that does is set up this. It sets up a positive chlorine. Now, chlorine itself is reactive and is electronegative. But how electronegative is a positive chlorine? Very electronegative. It wants electrons back. So the whole point of doing this is to try and help that chlorine break off. We're trying to make it leave. Now, you did some of this last semester when you tried the SN1, the SN2 reactions. When you did iodides and bromides, I think you used silver. You used Ag+, silver nitrate, to try and get the leaving group to break off. You've done those similar types of experiments. What we're trying to do here is generate this carbocation. Very simple way of doing so, which you've done. Now, this is my E+. Now, this system isn't a problem, but what is typically the problem with carbocations? They rearrange. They rearrange, and typically, or often, you can't really tell what products you're going to get with good sort of predictability, because you're getting carbocation rearrangements, which are not going to give you the same skeleton that you had in the starter materials. You're going to get a different skeleton. Now, in this example, it's no problem. What would this rearrange to, if anything? Is there any possibility to rearrange? And if it did rearrange, what type of carbocation would you get? You get the same, or at worst, you get a primary. So there is no benefit whatsoever for that carbocation rearrangement to take place. So now what we'll do is just attack it with the benzene system, and away we go in our typical reaction mechanism. So to do that, the alkylation starts with coordination of Cl with AlCl3, formation of a carbocation. Now, some of you in the room might end up doing these types of reactions for a living, so it's interesting to do this. You produce a carbocation. Carbocations need electron density. So now the nucleophilic benzene goes after that carbocation. We get a carbon-carbon bond formed. This is the beginning of, I would say, a huge number of carbon-carbon bond forming reactions that we have to worry about before now and the first week of May. In this example, it's similar to a Grignard, nucleophile attacking electrophile, but it's exclusively for benzene. We attack this thing and we get our resonance stabilized sigma complex, which is decent, but needs to become better by losing the proton to go back. And in this case, again, look how weak that base is, but how acidic this is, because the byproduct is HCl. And this example, you can get a good yield of that of that acyl, careful here, alkyl benzene, if you're careful. Now, there are two problems with this reaction. Number one is rearrangement. I'm trying to work out where I should stop. Number one is rearrangement, and number two is an argument about how reactive the product is versus the starter material. So here we have a problem. If you are trying to do this with a primary system, and you keep it simple like ethyl, it'll work. But what you won't get is a carbocation. Why not? Primary. Primary is terrible. Right? You don't really want to make carbocations primary if you can. So in this reaction between, all I've done here is change the substrate. We started out with maybe a sec butyl group there. Now I'm talking about a simple ethyl group. The chemistry will be similar in the sense that you'll coordinate the AlCl3 with the alkyl halide, and you'll produce the electrophilic species. But on the last slide, that chlorine broke off, because you were left with a secondary cation, which is fine. On this slide, no, because this isn't going to give you a good cation. But it still can react. And so what would happen here maybe is the nucleophile will go after that species and kick this out. Now, some of you are really starting to get your heads around this stuff. What mechanism does that remind you of? SN2, it does. An SN2 reaction, it certainly does. Same sort of idea. And you'll end up with the same sigma complex and go further, and you'll end up with that product. And all we're doing now is putting little mechanisms together to explain these bigger systems. Another example. Here, alkyl halide. The problem now is 35% of this, 65% of that. If that's the only way you can make it, maybe you're stuck, you have to distill, you have to separate, that's expensive. Or maybe you can work out a way to do this better, which is probably Monday by now. What's happening here is there's the original starter material incorporated into the benzene without any change in shape. Here, the major product has a change in shape. So this is where the primary carbon is added, and this is where the secondary carbon is added. So something has happened in that system to go from avoiding a primary carbocation to giving you a secondary one. And that's the problem with this reaction, the major product of this reaction. Problem. There's the first step, coordinate the AlCl3 with the chloroalkyl halide. Now, this second arrow, that arrow is simply avoiding the use of a primary carbocation. It is saying that the chlorine really badly wants to break off. Why? Because it's shared its pair of electrons with the Al, and it wants them back. And a positive chlorine is way more electronegative than a carbon, and so carbon's going to lose. If I break this off, if I simply use that arrow right there, I'll break all my rules, right? I'll have a primary carbocation when I can avoid that. If I'm building up a significant amount of delta positive charge on this carbon, then I ought to be able to shift this across to compensate. My hydrogen here is moving across simply to compensate. That's maybe a little bit new, but it shouldn't be anything more complicated than what you've seen. It's avoiding a primary cation by simply migrating at the same time that leaving group is breaking off. Keep an eye on that one. You get a secondary cation. You get the same mechanism now, because this is E+. You go after the secondary cation, and you get that secondary product. But the whole point here for the engineers is that that's a mixture, and we don't like mixtures, because they're expensive to separate. There will be a way of getting around that. Now, second problem. Right? A second problem. I'm going to, let's just use this. What do you know about alkyl groups? What do you know about, I don't know, Zaitsev? What was Zaitsev all about? What was better, a tetra-substituted alkene or a monosubstituted alkene? Tetra. Why was a tetra-substituted alkene better than a monosubstituted alkene? That's right. That's right. Somewhere between hyperconjugation and inductive effects, right? And the alkyl groups pushed electron density towards the alkene carbons, helping to stabilize them. So would you describe an alkyl group as electron donating or electron withdrawing? Electron donating. So I'm going to use this phrase or terminology for the first time maybe in detail. Electron donating group. Some of the things we've made are electron withdrawing groups. This is electron donating. Now you think about the competition here. You've got a system in which benzene is reacting with this alkyl halide, and it's getting consumed over time. The benzene is being consumed, and you're producing these alkyl benzene products. But then it's a competition between the benzene that's left and the alkyl benzene that you've made for the reagent. In other words, you might expect this to go after this, and this to go after this. And the problem is the product reacts faster. If you have an alkyl group on the benzene ring and it's pushing electron density into that cycle, you're making that cycle more nucleophilic. You're making that cycle more electron rich because you're pushing electrons into it. So the problem here again is that the product is more reactive than the starting material. If that happens, you end up with the product alkylating again. And you might end up with dialkylation, trialkylation. You get this horrible mixture. So the key point there is that these types of reactions are not particularly useful. And we have ways of getting around them. We will have other ways of making this in the near future. So to finish off today, let's make sure we understand what this is about in terms of alkylating, what the limitations are, and then we come back on Monday and do the acylation in which we solve the problem. So benzene is not going to react with this mixture. Why not? You can't form a carbocation on that system, right? And we've never done substitution chemistry on vinyl groups like that. It's always been on sp3 carbons. Likewise at the bottom, these two are not going to react. You're not going to be able to break this chlorine off here. This is an sp2 carbon, it won't allow it to happen. That's one of the major limitations right there. But then, the overalkylation argument. This is my last slide for today, I think, and then we'll come back on Monday. This is the overalkylation issue. What's happened here is that we've gotten a mixture here where we've generated tertiary carbocation. That carbon right there is tertiary. And if we drag that chlorine off and make a tertiary carbocation, yes, it's reactive, the benzene will go after it. And you will make a product in which one of these groups is now present. Simple alkylation chemistry through the same mechanism. But it turns out you get the majority of the product is this, with two groups on there. And there are two things to think about, thinking about your weekend. Number one, why is there a second group? And number two, why is it right there? Why is it in that position, nowhere else? So to answer the first question, this is electron donating. When we're trying to make this bond in the second reaction, we're not trying to make it, it works, it happens. That benzene ring with one group unattached is more reactive than the benzene you started with. So it competes with the benzene and it alkylates again. That's where you get over-alkylation. You get too many alkyl groups on there. But then the second question, which really leads into the big deal next week, why has it gone here? Why not go here? Steric environment. Way too crowded in that position. So you've got a lot to think about. Don't buy any washing machines this weekend. Leave that to me. You study. If you need your washing done, see Pierce. Have a nice weekend.